So I present a joint work with Ling Shen on learning when to advise human decision makers. In this work, so we consider a setting in which we have a human who needs to make a decision, and he's assisted by some algorithmic system for making this decision. And we have such algorithmic systems applied in a wide range of domains, like in the criminal justice system, in healthcare, in human services, and other domains. So we're thinking here about a settings in which human judgment is considered important. So the algorithm is not intended to replace the human, but only to help him reach better decisions. And in this kind of settings, decisions are often based on assessments of risk. So machine learning algorithms are being used to make risk predictions, and these predictions are then given as advice to the human decision makers. Let's take, for example, the pretrial release decisions that judges make in courts. Here, when a criminal defendant is brought in front of a judge, the judge needs to decide whether to release the defendant until his trial or to keep him in jail. And this decision also depends on the judge's assessment of how likely the defendant is, if released, to violate his release terms, which means here to commit another crime until his trial or to fail to appear in court for his trial. And for making such risk predictions, so judges in the US are assisted by pretrial risk assessment tools that use machine learning algorithms to generate some risk assessments, risk score for each defendant. So the judge observes the case of the defendant, this algorithmic risk assessment, and makes his judgment. And this is, of course, a very important decision to make for the defendant himself, for society. There was a lot of research around these risk assessment tools. Here it's going to be an example to demonstrate what we talk about in this work. So in this area of AI-assisted decision-making, there are works that focus on the algorithmic system itself, making all the optimization to reach the best algorithmic performance. And that's independently of the human, where the expectation is that, okay, we need we need good algorithmic performance in order to also have good human decisions. And the second, more recent line of works focus on the human user and studied how does this algorithmic input affect the decisions that people make. And what we typically see in these works is that algorithmic risk assessment improves human decision-making, and also that the way in which the algorithmic risk assessment is provided to the human also can have a significant impact on the human's decisions. And the work that I'm talking about now, so it's related to this second line of work. And what we suggest is to ask, when should algorithms provide advice? Because the current practice is that the algorithmic input has become a constant element in the decision-making process, which means that the human decision maker, so every time he needs to make a prediction or decision, so together with the description of the problem, he also observes this algorithmic risk assessment, combines these two inputs together to reach his decision. But we say that maybe we don't want to give this algorithmic input to the human every time he makes decision. Maybe this should depend on what the human can do on his own without the algorithmic assistance. So we suggest to use a responsive advising approach to provide the advice only when it is expected to improve the human's decision. So the questions that we ask are, can we train algorithms to automatically identify the cases where advice is useful? And does this approach indeed manage to improve human decision performance? Does it actually help? And here are several points that motivated this study. The first is about human AI complementary strength, because we know that algorithms are not perfect, they can have errors, and sometimes the human can reach better decisions on his own without the algorithmic assistance. So for example, we looked at the data set from an experiment that Green and Shen ran in their CSEW paper. And in that experiment, they let people on Mechanical Turk to make risk predictions for different cases of criminal defendants, and they compared several algorithmic assistance methods. And the best human prediction performance, so they observed it under a treatment that they called the update treatment. And in that treatment, so the human, after observing the description of the defendant, he made an initial prediction on his own, only then observed his algorithmic risk assessment, could update his prediction if he wanted to, and to set his final prediction. And this treatment led to the best human prediction performance compared to also letting the human predict on his own. However, we still see that in a significant fraction of the predictions, the initial predictions the human made was already more accurate than the algorithmic predictions. And in fact, many times, so the human, after seeing this advice, so he updated in the wrong direction. So the performance got worse in many cases. So this suggests that algorithms should be aware of what their human counterpart can do without this algorithmic assistance, and help and give this advice only when they can help. Ideally, what we would like to have is decision structures that utilize the complementary strength of the human and the AI. And the second point is that many times in these kind of settings, the expectation from the human is in some sense to monitor the input that he gets from the algorithm, which, like we said, can have errors. But there is a lot of empirical evidence that suggests that people are better at monitoring the quality of algorithmic predictions and determining when to override those predictions. So this may suggest to think about alternative designs that, instead of giving the human monitoring the algorithm, to transfer this to the algorithmic side. And the third point is that from a behavioral perspective, it is not clear whether constantly providing this algorithmic assistance is the best way to interact with the human when we try to help him make better decisions. Maybe this can result in the human paying less attention to this algorithmic input, or even ignore it when making his judgment. And the last point is that although what we typically see in these settings, that a human assisted by an algorithm reaches better decisions than what it could do alone, this joint behavior is still typically inferior to what the algorithm achieves alone, which I think is quite surprising, because in principle, the human could just do whatever the algorithm recommends and reach this algorithmic performance. So this suggests that there is something in the interaction between the human and the algorithm that could be improved. Okay, so here we see a diagram of this responsive algorithmic advising that we suggest to use. We suggest to use something like this algorithmic assistant here. So it is composed of this risk assessment algorithm that we already have. And it also has this advising policy, which is the component that we want to learn from data, that is responsible to decide whether to give the algorithmic risk assessment to the human. And how does it work? So, for example, when a new criminal defendant arrives, the human observes the description of the defendant, predicts his likelihood to violate his release terms. If released, this is Y-hat unassisted. And then given the description of the defendant and this unassisted prediction the human made, so the algorithmic assistant, it will generate Y-hat alg, which is an algorithmic risk assessment, and will provide it according to what the advising policy will determine, and it will provide it to the human only when it predicts that it is more accurate than Y-hat unassisted, the predictions the human made. And in cases in which it is not provided, so the final prediction is just set to this unassisted prediction. And when it is provided, the human observes Y-hat alg, can change his predictions if he wants to. This is Y-hat assisted, and that's going to be the final prediction. Now, note that there is a two-sided interaction here. So the algorithm is not just blindly advising the human, but it responds to what the human predicts alone. So we add this path of information from the human to the algorithm. So the information does not only flow from the algorithm to the human, but now also goes in the other direction. And in our implementation, this interaction is minimal, really. There is only a single bit of information passing from the human to the algorithm, this Y-hat unassisted, the prediction the human makes alone. And the second point I wanted to mention is that note that the way that it works is that the human operates on his own and makes predictions, and the algorithm is there to catch bad predictions that the human made. So now we have the algorithm monitoring the human instead of the other way around. And as the risk assessment algorithm, we just use the model from Green and Shen from the SIGecom paper. They trained the model on data from the US Department of Justice that included descriptions of defendants with 0-1 labels that indicated whether the defendant violated his release terms. And the output is y hat ag. This is a number between 0 and 1 that represents the likelihood that the algorithm predicts that the defendant will violate his release terms, like we said. And in this data set, in about 30% of the defendant cases, so they turned out to be risky, like to violate their release terms. And for training the advising policy, so we train a binary classifier on data of predictions that people made in a previous experiment. This is from a different experiment that Green and Shen ran in their FAT paper. And here again, they let people on Mechanical Turk make predictions for different cases of criminal defendants, compare different advising approaches. And we just took the data from their control treatment in which people just made predictions on their own without any algorithmic assistance. So the input to this advising policy, it is the description of the defendant, the algorithmic risk assessment, and this prediction the human made by himself. And the output, the label is set to advise if the algorithm is strictly more accurate than the human, and otherwise do not advise. In this data set, in 1/3 of the predictions, the algorithm's prediction was more accurate than the human's prediction, so the advice was supposed to be given in 1/3 of the times. And we ran an experiment on Mechanical Turk to see how people make predictions with the help of this advising policy. We wanted to see how they actually interact with it when making predictions. So here in this experiment, each participant was asked to predict the risk for a series of 50 defendant cases. Each one was randomly assigned to one of these 5 treatments that we compared. In all of them, the predictions that the human made was according to this pipeline that we saw. So in all of them, they saw this description of the defendant, made their initial unassisted prediction, and then got this algorithmic risk assessment according to the different advising policies. In what we call the learned treatment, so here we just use this advising policy that we learned from data that gives the advice when it predicts that it is likely to be more accurate than the predictions the human made. In random, we give the advice at random times, and that's in the same frequency in which the advising policy gave the advice on the training data. Omniscient, this is a treatment where the advice is given exactly at the right times, and that's when the algorithm is more accurate than the human, according to the ground truth. So here it's as if we could do some perfect learning, perfectly learn this when to advise policy. So here we just focus, put this learning aspect aside and focus on human response to this advice. So it's like upper bound on learning performance. In the no advice benchmark, we give people, they just make predictions without any algorithmic assistance. And we also ran this update treatment from Green and Shen in their CSCW papers. So here, every time after the human made his initial prediction, we always observe this algorithmic risk assessment. And this treatment led to the best human performance in this paper, in the CSCW paper, and in several other studies. So we compare with this as the always advising approach. Okay, so now let's see the results from this experiment. Here we see the learning performance. We want to see whether we managed to learn this advising policy to give the advice in the correct times. So we see that the advising policy gave the advice at the correct times more frequently than in the other benchmarks, except for the omniscient treatment, which by definition has a perfect accuracy. So we did learn to some extent, and we're able to generalize from this fixed training data where people just made predictions on their own to this new experiment where they interacted with this algorithmic advising and made predictions with this help. But whether 74.1% is good enough, so I think the question is if it managed to help people make predictions, better predictions, and that's what we see here in this. Here we see the human prediction performance according to two measures that we use for that. On the left, it's according to the linear score, 1 minus absolute L, and on the right, it's according to quadratic score. So let's look at the learned treatment here. We see that when participants were using this advising policy that we learned from data, so they achieved better performance than in the no advice, update, and random treatments, according to both score measures. Here we see the ranking of performance from best to worst. So it seems that selectively giving the advice in the learned treatment was better than help that people make better predictions than always getting this advice. This is in the update treatment. And the advantage of learned over the random treatment suggests that it is not enough just to give the advice in part of the times, but we need to do that in the correct time. And when we perfectly do that in the correct time, this is the omniscient treatment. So here, people manage to get the best performance. And when we compare participants in learned to the algorithmic performance, we see that which one is better depends on the measure that we are looking at. According to the linear score, we see that participants in learned had better performance than the algorithm. According to quadratic score, the algorithm was better. So this seems to be, so this is better than, for example, the update treatment, which is inferior to the algorithm according to both measures, which is what we typically see in these kind of settings. Omniscient treatment, which, like we said, it's only an upper bound on this learning performance. So we see a significant improvement compared to the algorithm according to both measures. This is maybe what we really want to have when we have a human joins forces with an algorithm. We want the joint performance to be better than the human alone and the algorithm alone. So for the omniscient treatment, we get it for both measures. For the learned treatment, we have it only according to the linear score. And now I'm gonna show some more findings that I think that are interesting about the way that people interact, that the participants in the experiment interact with the algorithm. So let's start with this human responsiveness to the advice. We found an interesting phenomenon that we call the scarcity effect. What we see here is human responsiveness to the advice according to two measures that we use for that, according to the advice acceptance rate and advice influence as a function of the frequency in which the advice was given. And we see that human responsiveness to the advice is negatively correlated with advice frequency. And so what it means is that when people get the advice less frequently, they tend to have a stronger response to the advice, to accept it to a greater extent, which I think is quite intuitive. I mean, it makes sense. We wouldn't want to tell somebody to do something too often. Eventually, he won't listen to us. But so we tried to find something like this in behavioral literature. We couldn't find something like this. I think it will be interesting to study this further. Yeah. Maybe also in the context of working with algorithmic assistants of this type. And we also wanted to ask whether, if with the human learning, whether participants in the experiment managed to make better predictions in this repeated interaction. So to see that, we compared the unassisted predictions human made with the algorithmic risk assessment, which is the only kind of feedback that participants got in this experiment and could learn from. So what you see here in the y-axis, we see humans' unassisted prediction, the percentage of times in which the human's unassisted prediction was at least as accurate as the algorithmic prediction. On the left, it's overall predictions in the experiment for each treatment. On the right, it compares first and second halves of the experiment. So we do see that when people don't get any algorithmic assistance, this frequency is the lowest. It is higher in all other treatments where they do get algorithmic assistance. It is the highest in the learned and omniscient treatments. And only in learned and omniscient, there is a significant increase from first to second halves. So this suggests that when working with the algorithm, getting this algorithmic assistance, so people learn and make better predictions. These are the unassisted predictions, make better predictions with respect to this algorithmic feedback. And I think that it's interesting to look at this learning effect over time. Again, we see that only for learned and omniscient over time. The x-axis is the prediction period. In blue, we see the same measure we just saw. This is the percentage of times in which the human was at least as accurate as the algorithm. And in red, it's the advice frequency. So what we see here is that as the human's unassisted prediction improves compared to the algorithm, so the advising policy it responds to this, it provides the advice less frequently, decrease in the frequency in which it gives the advice. So I think it demonstrates this responsive algorithmic advising thing. And we also looked at, how am I with the time? We also looked at the predictions at the aggregate level. And so what we see here is the histograms of the unassisted predictions that people made. This is in green. In blue, these are the predictions the algorithm made in the no advice, learned, and update treatments. So on the left, you can see that when people didn't have any algorithmic assistance, so their prediction behavior was quite different from that of the algorithm. On the right, you see that when they always got this algorithmic assistance, so the prediction behavior became much more similar to the algorithm. And in the middle, we see that when they only got the advice only in selected times, so the prediction behavior is more similar to that of the algorithm, but it's somewhere in between these two extremes. So this suggests some imitation effects that when people work with algorithm like that, so they learn to predict values that are more similar to the algorithmic predictions. And this may raise a concern that when people are exposed to the algorithmic assistance all the time, so they might internalize algorithms' behavior, including its weaknesses and biases, and perhaps also at the cost of losing their own relative strengths compared to the algorithm in making predictions. So there is a tension or a trade-off between, on the one hand, being able to learn from the algorithm and to make better predictions, and on the other hand, to preserve relative strength. And I think that there is one example that is interesting to see and is visible here in these figures. What we see here is that the prediction of a risk of 0. And this is, we call it the human relative strength, because the algorithm, it never predicts 0 here. It was trained to minimize squared error, so this makes sense. But the human here in the no advice treatment, when it doesn't have any algorithmic assistance, so it predicts a risk of 0 in quite a lot, in 10% of the times. On the right, we see that when people get the algorithmic assistance all the time, they learn to almost never predict a risk of 0, like the algorithm does. Which also makes sense, because every time after they predicted a risk of 0, so they saw something else that the algorithm says. In the middle, we see that when they got the advice at the selected time, so they preserve this relative strength. They predict a risk of 0 in a similar frequency to that in the no advice treatments, and like in the no advice treatment. So these are good predictions, like better than their average performance. So maybe when we try to optimize this trade-off, to think how to optimize between learning from the algorithm on the one hand and preserving relative strength, so selectively giving the advice can help. And in the paper, we also have a section where we analyze predictions that people made with respect to defendants' racial groups. I don't think that I'll get into this now. I think that I can now summarize. Okay, so we suggested to use a responsive advising approach to this setting where the algorithm assists a human decision maker to selectively give the advice depending on what the human can do on his own without algorithmic assistance. And the experimental results suggest this improves human decision making compared to always providing the algorithmic assistance and achieves comparable performance to the algorithm. And this improvement suggests that useful when-to-advise policies can be learned from existing data. And we also saw several behavioral observations about the interaction between how people interact with the algorithmic assistance that I think that will be interesting to study further about the scarcity effect that connects between the frequency in which people get this algorithmic assistance to the extent to which they follow, they accept this this assistance. So this is something that I think that there could be many possible sources to this effect that I think will be interesting to study. And also about human learning, that when people learn work with algorithm like that, he learns to predict values that are similar to what the algorithm does. So there is a change in behavior that maybe we should take into account when we design such systems and also deploy them. And we talked about this trade-off between learning from the algorithm to give better predictions and preserving human relative strength. And what we did here is minimal in the sense of this interaction between the human and the algorithm. I think that there could be many other interesting things to try there, richer interaction settings with the algorithm. And of course, to try to find it, to try that with human experts to see how this can work with people actually in practice. So that's it, I think.